All right, this will be the second of two video segments dealing with infrared spectroscopy. Right. So first, let's recall a couple things from the previous video. First up, some selection rules. Right. The vibrational selection rules say that the dipole moment of the molecule must change as the vibration takes place. Today, we'll look a little bit at what happens for polyatomic molecules. We'll look at CO2 in particular, and so we'll need to return to that idea that it's not that the molecule has to have a dipole moment, but that the dipole moment has to change as it vibrates, and we'll use that when we think about CO2. And for a harmonic oscillator case, we have that the quantum number, which is written there as n. Unfortunately, I'm going to actually just change that and make that say v. Because I've been trying to use V for the vibrational quantum number to keep straight which one is which a little bit better for us, right? That delta V change has to be plus or minus 1, okay? We will see in today's discussion that other transitions are possible for an anharmonic oscillator, which real molecules actually are, and so we can sometimes, although it's difficult, see other transitions than that delta V equals plus or minus 1. Rotationally, the molecule needs to have a permanent dipole moment to see a pure rotational spectrum. That doesn't mean we can't see rotational lines in a vibrational spectrum anyway, if there's not a permanent dipole moment, but it means we can't take a microwave spectrum of just rotational excitation on its own for a molecule that doesn't have a permanent dipole, okay? Again, CO2 will be an example of that. And for the rotational transitions, the selection rules are delta J and delta M sub J, both equal plus or minus 1. All right. The delta J1 shows up in our spectra. The delta MJ condition really doesn't very much show up because the MJ states are degenerate in energy, right? And so we can't tell the difference in those anyway in the spectrum. And so that one, unless we're doing something unusual involving magnetic fields, that one doesn't really influence what the spectrum looks like. So first up, I'm going to talk a little bit about anharmonicity, okay? And so this is a figure that we looked at before, right at the end, I think, of talking about the harmonic oscillator. I mentioned that real molecules actually are noticeably anharmonic, at least at higher energies, right? This is a calculated energy curve for a hydrogen molecule. And the thing about this is the molecule is not harmonic because the bond would eventually break, right? If we stretch the bond far enough, we'll tear the atoms apart from one another and break the molecule in half. And that's reflected in the fact that when I get up to high enough energies up here, my potential well just goes flat, meaning the atoms are free to separate, okay? The harmonic oscillator part does work well at the bottom of the well, right? And remember, in a harmonic oscillator, these energy gaps, the separation between adjacent levels, are supposed to be equal. And down at the lower energy states, the lower vibrational levels, they really are pretty equal. The model is good down there. You can see, however, here, though, that if you get up near the top, that my separations are getting gradually smaller as you climb the ladder, right? And so the vibrational energy levels get closer together as we go up in energy for the anharmonic oscillator. Okay, we're about to look at some experimental results that will confirm that we can see that by looking at some spectra. If we wanted to describe that anharmonic oscillator, it is usually done with an equation that says the energies are in the form listed here, right? The V plus 1/2 piece, this one actually is what we would get, this is the harmonic part, right? And then this piece, which has in it this chi-e part, that is the anharmonic term, right? And so that says that the energy for the vibrational state will be reduced a little bit for that, and the amount it will be reduced by that second term increases as V goes up, right? So that is what causes those levels, or what justifies the idea that those levels are getting closer together. This particular form and this parameter over here, these are usually found just by an empirical fit. So you take a spectrum and you fit the data and get a value for that anharmonicity constant over there, written as a chi in this case. All right, we're not going to actually work actively with that equation. I did just want to mention that there is at least an empirical model that does fit the form of the real molecule potential. So when we look at spectra taken at room temperature, I didn't really talk about this, I guess, in the previous video, and maybe I should have. It turns out that in general, for spectra taken near room temperature, we tend to only see peaks that correspond to transitions that start from V equals 0. Okay, and the reason for that is that at room temperature, something very close to all the molecules are in V equals 0. Right? The vibrational energy levels are far enough apart that in a normal sample of gas around room temperature, there are very few molecules that are vibrationally excited. Okay, and so if we were to look at a hot spectrum, then we could begin to see things that were higher up. Okay. Another way to see the higher vibrational levels is to try and look at what are referred to as overtone peaks, peaks for which delta V is greater than 1. Okay, and if we do that, this is just sort of like a bar graph where this part here, what's labeled as fundamental, this is for HCl, I think. Yes, those are the HCl numbers. Right, and the height of that initial peak, that just says that's like the total absorption intensity for that set of transitions starting from V equals 0. Okay, if I go to or going from V equals 0 to V equals 1, sorry. If I go to the first overtone, this is V equals 0. I drew 2 zeros, that was dumb. V equals 0. And this goes to V equals 2. This one is up to V equals 3. This one is up to V equals 4, and so on, right? And if we do that, if we actually look at those wave numbers that are attached to them, we will be able to see what happens as these go, right? Notice as I show this that the intensity is getting much smaller as we go higher up. That these peaks get much harder to measure as you go because we're breaking that harmonic oscillator selection rule, right? And the probability for this transition is much less, and so we see a much smaller intensity for that. Here are the numbers for those observed transitions. These are the energies that are actually observed, okay? And these are the energies if we had a harmonic oscillator. So if it was a harmonic oscillator, then essentially we would just keep multiplying, right? This number here, the first harmonic, that would be just 2 times the fundamental, right? Because the spacings would be the same. And so my numbers going across the top row there are just successive multiples of the original harmonic oscillator frequency. Notice that even the first transition is a little bit off from that, right? It's not perfectly harmonic even in the bottom, right? But as I go up, the higher up in these overtones I go, the further apart these 2 numbers get, right? So these are separated by, I don't know, about 5 wave numbers, let's say. I get over here and now I'm different by 27 wave numbers, right? Come out here and I'm now different by, that's not 27 wave numbers. No, that's more than 100, right? Sorry, I missed the important part. This one, 59, 80 minus 56, 60, right? So that would be almost 300 wave numbers. Here I am now different by over 600 wave numbers. Out here I'm different by 1,000 wave numbers, and so on. Okay, and so we can see that they really do get closer together. The energy levels get closer together as you go up, because that's why these things are getting smaller than the predicted multiples. That anharmonicity constant, then there's a value for that. That's not important really in any way. It just says that we could actually fit that form of the curve to the data from here. For the remainder of today's video, what I'm going to talk about is a little bit about vibrations in polyatomic molecules. Polyatomic here just means anything more than 2 atoms. Okay, if I have a larger molecule, the spectra get more complicated because there are now different vibrational motions possible. okay? The number of different vibrations is going to be connected to the degrees of freedom, right? We said in the previous video that there are 3 n degrees of freedom overall. Out of those, 3 of those are translation, right? And then we have rotations. The number of rotations is 2 for a linear molecule, and we talked about that last time, the fact that there's no rotation about the 3rd axis, because that would be the one that is the line of centers of the molecule, where there's no moment of inertia. So if a molecule is linear, then it has 2 rotations plus 3 translations, that's 5. That means there are 3n minus 5 left over to be vibrations. If the molecule is nonlinear, then there's 3 translations and 3 rotations, and so 3n minus 6 would be the number of vibrations in that case. These are sometimes referred to as, quote, normal modes, and the way they're described is related to the symmetry of the structure of the molecule and things like that. We're not going to look at too much detail of that. We will look at CO2 as an example, just to see how we can talk about the different vibrational motions and how they influence what peaks do and don't show up in spectra. So the carbon dioxide molecule is linear, right? If you draw a Lewis structure for it, it's just carbon in the center, double bonds to the 2 oxygens, right? So it's a nice and symmetric looking molecule. N here is 3, so 3n is 9. It's linear, so 3n minus 5 says I get 4 vibrations, right? That's the number we should expect. Those vibrational modes are illustrated by these sets of arrows over there on the screen. Remember, to be a vibrational mode, the center of mass has to be fixed, right? Movement of the center of mass is what we call translation, and so that can't take place in my vibrations. If I look at these, excuse me, the one on top is what's known as a symmetric stretch. And so I usually try and do these things with my hands, which I can do at least a little bit here on the camera, I think. And so if my thumbs are the carbon and my fingers are the oxygens here, in the symmetric stretch, the 2 carbon-oxygen bonds both get longer and both get shorter at the same time and in phase with one another, right? It's called symmetric stretch because the molecule itself is always symmetric, right? The center of mass doesn't move because the center of mass is the carbon atom when it's in just the normal linear configuration, and I'm only stretching the oxygens away and squeezing them closer, right? That's my symmetric stretch. The energy for that turns out to be, as it says there, about 1388 wave numbers. That vibration should not show up in an infrared spectrum. And the reason for that is because at any position along that vibration, the dipole moment is always 0 because the molecule is always totally symmetric, right? The carbon is always exactly at the midpoint between the 2 oxygens. And so there is no reason why it would change the dipole moment. There are a set of 2 degenerate bending vibrations, which says the molecule is originally linear, right? So now if the intersection of my fingers is the carbon atom, and going up my fingers makes the oxygens, picture one of those bending modes as one that would bend it like this, okay? So it's bending in a plane that right now is perpendicular to the direction of the camera or parallel to the screen. Right. The second bending vibration would then be in a plane that is perpendicular to the screen, which means it's very hard for me to do usefully with my fingers, but I'll be bending towards me and away from me, or towards you and away from you. Okay. You'll notice in the drawing for this one, here the oxygens move down a little bit and the carbon moves up some. That's because the total motion has to keep the center of mass fixed. Right, and so to do that, I can't only move the oxygens, because if I do that, I would have shifted the center of mass. Those are at a smaller energy, about 667 wave numbers. That's usually true, that bending, distorting a bond angle is usually a little bit easier than stretching a bond in a molecule, right? And then the last vibration is the one that is actually the most responsible for CO2 absorbing infrared radiation and the whole greenhouse gas effect and all that. This is what's known as the asymmetric stretch, okay? So now again, my thumbs are the carbon, my fingers are the oxygens. In the asymmetric stretch, one bond is getting longer while the other one is getting shorter, okay? So it would go something like that. And again, the carbon has to shift some in order to keep the center of mass from moving, right? If I really just did this, I would have shifted the center of mass. And so to do that, the carbon has to move towards the shrinking bond on the short side, okay? That vibration and the bending vibrations are definitely active in the IR because they're gonna be changing the dipole moment, right? When the molecule is bent, it would have a dipole moment. When it is straight, it would not. The asymmetric stretch would also give rise to a change in the dipole moment, right? Because in the normal position, the CO2 is symmetric, but once I make it asymmetric, there's going to be a bond dipole associated with those bonds, and they're going to be different when the bond lengths are different from each other. So because the two bond lengths change differently in this vibration, I would get an IR active vibration, and that one is at about 2349 wave numbers, okay? That is a very, very strong absorption spectrum because it's got a very large change in the dipole moment, and that helps to boost its absorption strength. Let's take a look at what the spectrum would look like for that asymmetric stretch vibration. This is the CO2 asymmetric stretch, and you can see that it looks in a general sort of way similar to the HCl spectrum, right? It has, let's see, this is now the low energy side over here, and this is the high energy side over there. So we flipped directions from the previous one, all right? This side of things, on the high energy side, these are the transitions where the rotational part is delta J equals +1 over here. These are the delta J equals -1. I again would have my missing Q branch in the middle. All right. You can see down below, I've got this second envelope here of some second set of peaks. Those actually are going to be from a small trace of isotopically substituted molecule, right? There's about 1% carbon-13 in normal carbon, and that looks like that's going to be the part that comes from there. There's a lot less than that of oxygen-18, so it wouldn't make sense for it to be that. And so I can see that in these spectra. I'm not sure if I mentioned this in the previous video, but the reason why the heights of the different peaks are different is just because the number of molecules in the different J states are different, right? So in this region of things here, where I get the tallest peaks, those in general will just correspond to the rotational states that had the most molecules in them when the sample was just sitting there getting ready to absorb the light, right? Because the more molecules are in that state, after all, the more can possibly absorb that particular energy, right? By the time I get way out here in the wings, I'm not going to count all those peaks, but by the time I get out there, it looks like I'm probably up to J equals 20 something or more. And by that point, there are very few molecules that are that high up that rotational ladder. That's why I see very small peaks there, right? When we move into chapter 5, which we will do shortly, we'll be taking up statistical mechanics, and that will give us the tools we need to actually calculate some information about populations of those different states. And once we've got those things in our toolbox, we will probably come back and take a look at these spectra again, where we can make a better justification of why the peaks that are taller are the ones that they are. Okay, but this shows us that the spectrum still looks very similar. We could, from this spectrum, once again, we could find things like the bond lengths and what have you for the molecule as well. All right. Right, that wraps up our, for now, our discussion of infrared spectra. Right, as I just mentioned, we will come back to this idea once we have a few more tricks available to us from statistical mechanics to look at populations. The remaining video for this particular module will deal a little bit with electronic transitions and how we can, at least in some circumstances, use the particle in a box model in particular as a model to attempt to understand electronic spectra. Thanks.